So we'll continue our discussion about the third voltage regulation method. In the last two classes, we have discussed about EMF method, and second one is MMF method of voltage regulation. Even we solved about the numerical problems of EMF as well as MMF methods. Now we will try to discuss about the third method is zero power factor method. If you can recall that EMF method, the percentage voltage regulation, okay, measured, we are getting more than the actual, okay, percentage voltage regulation. Whereas MMF method, the percentage voltage regulation measured will be less than the percentage voltage regulation actual. So though both has certain drawbacks here. So in EMF method, we only consider the entire synchronous reactance as leakage reactance, okay, and whereas in MMF method, entire synchronous reactance is considered as armature reactance. So because of this, 1% voltage regulation we are getting more than, and other percentage voltage regulation we are getting less than that here. So this is the percentage voltage regulation. What is the formula that we can able to see this? Okay. Percentage voltage regulation E naught minus V by V into 100. Okay, E naught minus V by V into 100 here. Next, here we'll try to discuss the steps. Okay, we'll try to discuss the steps of zero power factor method here. So for this, what we require here, we require open circuit characteristics as well as zero power factor characteristics. Open circuit characteristics are drawn between E naught versus IF. ZPFC characteristics are drawn between V versus, okay, IF. Okay, so open circuit characteristics, we will try to draw open circuit characteristics as well as zero power factor characteristics from the given readings here. Okay, from the given readings. So in what way this zero power factor characteristics are useful here? It gives the more accuracy compared to the other two voltage regulation methods. Zero power factor method is also called as POTIER triangle. POTIER triangle method. Okay. Open your spiral and write out those keys. You can hide it. In my opinion, that is okay. What do you find important? Try to note. Okay, so we're trying to, what is required, prerequisites for this here? We require open circuit characteristics as well as zero power factor characteristics here. Okay, so now in addition to this, so we have this XS equal to XA plus XL. Okay, XS equal to XA plus XL. So here in this method we are considering both. In this method we are considering both here. Okay, in this method we are considering both. In this method we are considering both XA as well as XS. So in EMF method we only considered as XL as a complete reactance here. In MMF method we considered only XA as complete synchronous reactance. Now whereas in ZPF method, what we are doing here, actually the synchronous reactance itself is a combination of armature reactance plus leakage reactance. Now whatever actually is there, we are considering separately, so that we can able to estimate the exact values here. Okay, so let's try to discuss the actual steps of the characteristics here. Just it's a quick recall here. How to find the open circuit characteristics as well as short circuit characteristics. So this is the stator, okay, which is connected in star connection. This is a stator which is connected in star connection. Okay, and this is DC supply. Okay, this is DC supply, and it is excited with this is the field winding which is excited with DC supply here, and these are open circuit characteristics as well as when the TPSC switch is open, this is open circuit characteristics. When TPSC switch is closed, this is short circuit characteristics here. In this manner we can able to measure the open circuit characteristics as well as short circuit characteristics here. Okay, next what is the purpose of prime mover here? As it is a generator here, mechanical energy is required, and we can able to provide the mechanical energy with the help of this prime mover. Okay, and just quickly draw the diagram fast. Okay, so similarly, we can even find out the zero power factor characteristics. We already discussed these characteristics in the last unit in detail here. Open circuit characteristics, short circuit characteristics, as well as zero power factor characteristics. To get the zero power factor characteristics, we must use which load here? Pure inductive load here. Pure inductive load here. The characteristics, everything is similar here. Okay, only thing is, so I am connecting this one is acts as a prime mover. Okay, you have separate experiment in machine slab. Okay, zero power factor characteristics here. So this motor is used as a prime mover to generate the mechanical energy in labs. Basically, in labs, we cannot able to get the mechanical energy directly. Yes or no? So for that reason, in labs, in order to provide or get the mechanical energy, we need to have a machine or equipment which can able to take any electrical input and give the mechanical input as a mechanical output as the output here. So what is the device which can able to give the electrical energy as input and mechanical energy as output here? DC motor. So I am using a DC motor which can able to take the electrical energy and giving the mechanical energy as the output. So this energy, what I am doing here, this one I am trying to consider. Okay, I am trying to give this motor as a mechanical energy as a prime mover to the alternator here. This alternator is connected in star connection, and same here and to this. And what is this here? This is field winding. Field winding is always excited with this supply here. DC supply. Field winding is always excited with DC supply here. Okay, field winding is always excited with DC supply. Now the load is connected. I am connecting a pure inductive load here, and once it is done here, I need to take the characteristics between V versus IF here. This is how we can able to draw the characteristics between characteristics for zero power factor characteristics. Why it is zero power factor? Because the load is pure inductive loads. We are connecting a pure inductive load here. As I am connecting a pure inductive load, the characteristics will be whatever we are obtaining here. Those characteristics can be called as zero power factor, ZPF flag, zero power factor, ZPFC, zero power factor characteristics here. Okay. Next, we will try to know the steps of procedure for drawing zero ZPFC method. Okay. First, I'll try to just go through in short, and we'll try to draw the characteristics of our graph separately. Okay. So here, what we'll try to do here, we'll try to draw OCC, ZPFC, and we'll try to draw air gap line. And next, we'll try to draw the dotted rated voltage. Next, we need to consider even the POTIER triangle. And after that, okay, there is a lengthy procedure is there. What we'll do here, we'll try to discuss simultaneously. Okay. Okay. So. Zero power factor characteristics. Okay, zero power factor ZPF method of finding percentage voltage regulation. Okay, now here the steps of procedure is already there in the written already there. Here I will try to draw. Okay, make use of this. Okay. We will try to draw an approximate diagram. Okay. This is between V versus IF. Okay. First, what I have to do here, first step is draw OCC characteristics. Draw OCC characteristics. Okay. Open circuit characteristics. Open circuit characteristics are drawn between what? E naught versus IF. As this is a voltage here, okay, I can consider the same as the E naught versus IF is the open circuit voltage here. You draw OCC characteristics, E naught versus IF here. And next, after that, I need to draw ZPF characteristics. Okay, in continuation to this open circuit characteristics here, so I can draw a tangent to the OCC. What is tangent or air gap line? We can say that what is air gap line here? So if there is no saturation, then the generated voltage, you can see that the voltage you can see that the voltage is slightly dropping here. Okay, it's not the linear characteristics here. So up to some extent, up to 100%, the characteristics are linear here. But beyond that, once it is causing certain point here, what is happening here? The characteristics are bending. It's okay, drooping here. It's because of the saturation of the magnetic saturation here. It's because of the magnetic saturation we can able to get the complete linear characteristics here. And what indirectly what is air gap line indicates that? Air gap line indicates that if there is no saturation, okay, then the ideal characteristics will be, what is the ideal characteristics will be? Those characteristics will be air gap line characteristics here. So here these will be, will normally represent as AG line, which represents that air gap line. AG represents that air gap line here. Okay, AG line represents that nothing but air gap line. Air gap line is nothing but, so I need to draw approximately air gap line. Okay, next. So after this, what we need to do here, again after I need to draw ZPFC curve here. I need to draw ZPFC curve here, zero power factor curves here. So after taking the reading, what are the experiments that we have done here for by conducting the connecting the alternator to the three-phase pure inductive load here, we can able to get this zero power factor characteristics here. Okay, we'll try to get the zero power factor characteristics here. Now after this, what I need to do here, I need to apply the rated voltage. Let's try to see here. I'll try to use different colors so that it's, so whatever the rated voltage is there given in the for the rated specifications here, I need to draw a rated voltage onto the ZPFC curve here. I need to draw a rated voltage onto the ZPFC curve here. Okay, draw a rated voltage. If that rated voltage is phase voltage is some 230. Okay, so always convert this rated voltage has to be in which manner? Phase manner. Convert the line voltage. What are the line voltages are there? Convert that into phase voltage and draw a dotted line onto the ZPFC curve here. And next here, give the notations here. From this, give the notations as OA. Okay, whatever the procedure is given just now. Okay, the notations might be slightly changed here. Okay, I'm not by hearting the things. Okay, I'm directly noting down directly here. This length I'm considering it as OA length here. Okay, this length I'm considering it as OA length. Now here, what are the intersection point is there here? This point I'm considering it as B here. What is the intersection point here? Intersection point of rated voltage onto ZPFC. Intersection point of OA onto the ZPFC here. Okay. So once it is done, okay. So ZPFC here. So once it is done, what I need to do here, whatever the OA length, take the scale, okay, take the scale, and let's assume that 1, 2, 3, 4, 5.3 centimeters are there. Okay, let's assume that whatever the OA length is there, take the same length and extend it from the B to its left side. If the length is, let's assume that this length is from 5.3 centimeters is there. So from the B point, draw a horizontal line onto the left side. From the B point, draw a horizontal line onto the left side. That means 1, 2, 3, 4, 5 and 5.3 here. Let's assume that here I'm drawing randomly here. This length is the same as that of the OA length. This length is same as that of the OA length. Give the notation as C here. Okay. Give the notation as C. I'm again saying that whatever the procedure is given, notations might be slightly different here. I'm not by hearting things. Whatever we get directly I'm writing here. Okay. So this length, okay, this one. So if you want to stick on to this, so okay, this length BCOA. Let's try to go with our original practice. No, not an issue. Okay. After this, what I need to do here, from point C, draw a line parallel to air gap line. From point C, draw a line parallel to air gap line. Take a scale, and whatever we see from the green line here, I have to draw a parallel line here. So even I will try to draw a line with a green line only. This line is how I am drawing here. This line is parallel to air gap line. This line is drawn parallel to air gap line. We have to draw in such a way that it should be able to intersect the OCC curve. It should be able to intersect the OCC curve. It should be able to intersect the OCC curve and give the notation as some point as D. Give the notation as D here onto the intersection point here. Give the notation as D here. And once the intersection point is given here, what I'm supposed to do here? Okay. Okay. And next draw D and B and draw a perpendicular point here. Just draw up to this extent. Okay, so and give the notation as this point as the intersection point, the perpendicular one is H here. Give the notation as H. Give the notation as H here. Okay. Now here, whatever the heading what we have discussed now, that it is ZPF method or there is one more name here, POTIER triangle method. ZPF method or POTIER triangle method. Okay. This one is the POTIER triangle. This one is the POTIER triangle, and because of this POTIER triangle, the name is also called as POTIER triangle method. Because of this, the name is also called as POTIER triangle method. Okay, so that the right angle triangle BDH is called as POTIER triangle method. Okay, so here once the POTIER triangle, how we are drawing here? So I am drawing OCC characteristics. I am drawing ZPFC. From that, I am drawing a rated voltage, phase voltage onto the ZPFC. From that, whatever the OA length is there, I am trying to draw same BC length. OA is equal to BC length, and from that next OA length is equal to BC length, and from the C point, draw a line parallel to air gap line such that it intersects the OCC. From the intersection point D here, extend the line onto the B as well as H. Okay, and this is how we are constructing the triangle called POTIER triangle. Now here this length is, I can be able to consider, there are two parameters here. I can be able to consider that directly. I can be able to get these values here. So IFA, IFL, and this one more thing is IAXL, this length. So here I am writing here DH is IA into XL drop. So leakage reactance drop. DH is, so just by graph we can able to obtain this length here, and IFA and IFL, okay, field current required to generate armature reactance drop. Okay, what is IFA here? So it's already there in this explanation. Just I am trying to tell you here. What is IFA here? Field current required to generate the armature reactance drop here. It is responsible component to generate the armature reactance. What is IFL here? It is a field current required to generate leakage reactance drop here. This field current required to generate leakage reactance drop. Just by POTIER triangle, we can able to get this data here. This length is DH length is IAXL drop here. This DH length is IAXL drop. Once after getting these values, what I am supposed to do here? Okay, this is the combination of, okay, this ZPF method. ZPF method is a combination of EMM method as well as MMM method. So in EMM method there is a drawback, and even in the MMM method there is a drawback. In EMM method, the voltage, percentage voltage regulation we are getting more than the actual. In MMM method we are getting percentage voltage regulation less than the actual here. So we are combining both methods so that to get the accurate value, to nearest to the measured value, actual value, to nearest to the actual value. So what I am doing here, first I will try to implement EMF method in this method. Okay, EMF method concept. So whatever the voltage formula is there for EMF method, same concept I am implementing here. So let's try to consider this as a case here. What is by using EMF method here? Okay, by using EMF method concept. By using EMF method concept here, we have, let's try to assume that I am assuming it as ER. It's not the final voltage here. Okay, normally we assume that directly E naught equal to the generator voltage or no load output voltage here. This is, I am considering it as the intermediate output, intermediate no load voltage. Let's see that. First, let me try to write down this formula here. It is V phase cos phi plus IARA whole square. Okay, it's not 18. Okay, V phase cos phi plus IARA whole square plus V phase sin phi plus or minus IA into XL whole square here. Okay, V phase sin phi into IA into XL whole square here. By using this formula, I need to find or calculate ER. By using this formula, calculate ER. Now, can we able to let's check that whether we know all these parameters or not. V phase, okay, rated phase voltage, rated phase voltage V phase equal to VL by root 3. Yes or no? We got this. Next, cos phi will be given, they will specify in the question. Cos phi will be given in the question. Let's assume that example 0.8 power factor lagging or leading. For lagging we have to plus and for leading we have to keep minus here. Okay, we have to keep minus here. Next, IA, rated current. IA is nothing but rated current. How can you able to get the rated current here? We have to calculate rated current. What is the formula here? IA equal to S by root 3 VL. IA equal to S by root 3 VL. Whether it's a star connection or delta connection, let's assume that this is a star connection. Okay, IA equal to I phase. Am I correct or wrong? So next, RA. What about RA here? RA given in question. Okay. Next, again V phase is already known. Sin phi, once we know cos phi, sin phi can easily calculate it. Next, IAXL. Now see that. Have you used this IAXL? Have you calculated this IAXL? So this IAXL, I mean to say this IAXL, whatever the IAXL is there, this is the corresponding voltage. Let's assume that here the voltage is some 50, here the voltage is some 250. Okay, so what is IAXL length value here? It is 250 volts minus 50, not 4 centimeters. 1, 2, 3, 4, 4.2 centimeters, not 4.2 centimeters. The scale length is 4.2 centimeters. Corresponding to that, what is the voltage here? So it is the corresponding voltage. What is the y-axis values are given here? We have to take the corresponding values here. So this is the difference between the D value minus H value. Okay, it is the DH length here. This is the IAXL drop. Whatever the IAXL drop is there, that I have to substitute here in the formula. IAXL drop, that is in voltage here. What is the corresponding here? Length we are getting here. Once we get this here, normally in the EMF method, by this the calculation is completed directly. We'll substitute here E naught. We'll substitute here E naught minus V by V into 100 and we'll get the percentage voltage regulation. But to get the more accurate value here, I'm not just stopping here. I'm considering this ER is intermediate value. I'm considering ER is intermediate value. Okay. So now here, up to now, what we are doing here, we are implementing which method? EMF method in ZPF. We are implementing EMF method in ZPF here. Once it is done here, now what I will do here, I will try to implement MMF method. How I will implement MMF method here? Whatever the ER value that I am getting here, okay, you can able to understand better, okay, 100% perfect once we solve a numerical. So whatever the ER value that we are getting here, we have to substitute in the graph here. I'm trying to use one new color here so that it will be easy. Okay, so let's assume that I got some ER value. This value is the ER length that I got. Okay, can you able to see this or not? So this is the ER length that I got here. What I need to do here, I have to this extrapolate. I'm using a term called extrapolate. So extrapolate is nothing but draw the dotted lines onto the OCC characteristics. Extrapolate is nothing but draw the dotted lines from this point. Draw the dotted lines onto the OCC characteristics here. You will get an intersection point. Am I correct or no? You will get an intersection point here. From there, again you have to draw a dotted line onto the x-axis, onto the field current here. From ER, whatever the ER that you got from the formula, you have to draw from that point, locate that point ER, draw the extended dotted line onto the OCC from that point here. Okay, draw a dotted line onto the y-axis. This current I am considering it as IFR. This field current I am considering it as IFR. There are already two currents are there. IFA is there, IFL is there. For MMM method, what we did, we considered IFA and IFL. Phasor sum of IFA and IFL is directly the resultant value. Okay, directly resultant field current, and from that field current we can able to directly interpret the OCC characteristics, and from that we can able to get the E0 here. Now here, whatever the ER that I got here, I am representing on the OCC. From that I am trying to find out IFR, corresponding field current here. So here from MMF, from ER to OCC, from OCC I am getting which current here? IFR. Now here, what is MMM method? MMM method finding the IFT. Previously we used to do phasor sum of IFA plus IFL. Now here, instead of phasor sum of IFA and IFL, I am replacing IFL with IFR. I am replacing IFL with IFR. So everything is same. So IFT is the phasor sum of IFA and IFL, which normally we used to do here. Instead of IFR, to get the more accurate value, I am implementing MMM method in ZPF by replacing IFL. Instead of IFL, I am replacing with IFR. Then the new formula will be, IFT formula will be IFA whole square, okay, IFR whole square, 2 into IFA into IFR into cos of 180 minus 90 plus or minus 3. We already use this formula here. Okay, you can simplify and you can extend, you can rewrite the formula as per our maths basic simple concepts here. So all silver teacups, you can reframe in it. I'm just using the one of the basic conclusions here. Okay, basic formula. Okay, IFA square plus, instead of IFL, what I'm writing here, IFR. How you got this IFR? From the ER. Where we got this ER? ER from the EMM method. Okay, EMM method formula here. IFA plus IFR plus 2 into IFA into IFR into cos of 180 minus 90 plus or minus 3. Where plus stands for lagging and minus stands for leading here. Plus stands for lagging and minus stands for leading here. Once we get this here, okay, locate, okay, calculate IFT. Once IFT is there here, this is the final value here. Okay, once that, and we have to draw locate IFT in graph and draw dotted lines onto the OCC curve here, and from that again extend the dotted line to where extend the dotted line onto y-axis, and where you will get the final value as E0. Let's try to show the same from the graph also. So I'll try to use one more color here. Okay. So what I'll do here, let's say that I got this value as IFT here. Okay. This value as IFT. From this point, what should I do here? Draw a dotted line here. Draw a dotted line onto y-axis, onto OCC curve here. There is an intersection point onto OCC. So whatever the intersection point is there, from that draw a dotted line onto y-axis, that value. So from I'm locating the IFT here. I'm locating IFT on the x-axis. From the draw a dotted line onto OCC, and from that point draw a dotted line onto y-axis. And this point I'm calling it as E0. This is the final E0. Okay. So previously we used to do only single calculation, either by using E0 V under root of V phase cos phi plus or plus IA or A whole square plus, okay, this formula, and directly getting the E0 final voltage. And even in the MMF also directly using this formula and getting the corresponding field current to get E0. And whereas in ZPF method I am combining both these two, so that the accurate value will be more here. So EMF method will try to measure, will try to corresponds to XL, okay, leakage reactance. and MMA method corresponds to XA reactance. So I am including both reactances here, XA reactance as well as XL reactance, so that the final value will be E naught. After getting final value, what is there here? Percentage voltage regulation. E naught minus V by V into 100. This is how we can able to get the percentage voltage regulation. Okay. Only change is, so if it is a lagging load, then instead of plus, I have to replace it with minus. So here also instead of plus, I have to replace it with minus here. Okay. So let's try to proceed what we discussed. Okay. So let's try to cross check what we discussed. Is it correct or wrong? First, what are the steps here? Have you drawn OCC, ZPFC? Next, we have drawn a dotted horizontal line onto ZPFC, and I have used it to intersection point of some P here. So I have used a BC equal to ALN. Next, draw a line parallel to air gap line. Next, join BD, direct perfect line. And I have considered these two currents here, IFA current, and there is one more current is called as IFL current. And I have considered this perpendicular length as IAXL drop. Whatever the IAXL drop is there, I have used this here formula. ER equal to, I am not considering this as a final value, I am considering this as the intermediate value here. So ER equal to, okay, P base cos phi, okay. Even if you get 25 also, we can have to consider this. Okay, next. After this, water corresponding to the ER, I have to draw into the OCC, and next find IFR here. The phasor sum of IFA plus IFR will give us the IFT. After getting the IFT here, locate the IFT onto the x-axis and to the OCC, and from OCC draw a dotted line onto the y-axis, and you will get the final value as E naught. Once we get the E naught here, you can able to get the measure the percentage voltage regulation. This is the corresponding graph will be. Okay, whatever the drop that I have drawn here. Okay, this is the corresponding graph here. You can see that first, if you want me to, first I have drawn OCC, next this is the air gap line, next this is the PFC line. Okay, and this is a dotted phase voltage here. You have to draw a dotted line here. What are the OA length is there? I have to consider from point E, and this length I have to draw similar to that OA length. From C, draw a line parallel to air gap line. From the intersection point, draw these two lines here. Okay, and this length is DH length is IAXL drop, and this one is BH is IFA, and this CH is IFL. So many times asked about these parameters, which branch, which base is corresponds to IFA, IFL and IAXL drop. Once we get this, use this formula IAXL drop, and using the formula V phase cos phi EMF method. Find out ER. From that ER again, okay, apply the MMF, find out IFR, and from that phasor sum of IFR and IFA will get IFT. Okay, this is how we'll try to get the conclusions here. Okay, so we'll try to solve numerical in the next class.